In 1932, the physicist James Chadwick conducted an experiment in which he bombarded beryllium with alpha particles from the natural radioactive decay of polonium. The resulting radiation showed a high penetration through a lead shield, which could not be explained via the particles known at that time.
James Chadwick was a British physicist who was awarded in 1935 Nobel Prize in Physics for his discovery of the neutron in 1932. He born in 20 October 1891. In 1941, he wrote the final draft of the MAUD report, which inspired the USA government to begin serious atomic bomb research efforts. He was the head of the British team that worked on the Manhattan Project during the Second World War. He was knighted in Britain in 1945 for his achievement in physics.
Chadwick graduated from the Victoria University of Manchester in 1911, where he studied under Ernest Rutherford, known as the father of nuclear physics. At Manchester, he continued to study under Rutherford until he was awarded his MSc in 1913. The same year, Chadwick was awarded an 1851 Research Fellowship from the Royal Commission for the Exhibition of 1851. He elected to study beta radiation under Hans Geiger in Berlin. Using Geiger's recently developed Geiger counter, Chadwick was able to demonstrate that beta radiation produced a continuous spectrum and not discrete lines as had been thought. Still in Germany, when World War I broke out in Europe, he spent the next 4 years in the Ruhleben internment camp. After the war, Chadwick followed Rutherford to the Cavendish Laboratory at the University of Cambridge, where Chadwick earned his Doctor of Philosophy degree under Rutherford's supervision from the Gonville and Caius College, Cambridge in June 1921. He was Rutherford's assistant director of research at the Cavendish Laboratory for over a decade, at a time when it was one of the world's
Cavendish Laboratory at the University of Cambridge, where Chadwick earned his Doctor of Philosophy degree under the Rutherford supervision from Gonville and Caius College, Cambridge in June 1921. He was Rutherford's assistant director of research at the Cavendish Laboratory for over a decade, at a time when it was one of the world's foremost centers for the study of physics, attracting students like John Cockcroft, Norman Feather, and Mark Oliphant. Chadwick followed his discovery of the neutron by measuring its mass. He anticipated that neutrons would become a major weapon in the fight against cancer. Chadwick left the Cavendish Laboratory in 1935 to become a professor of physics at the University of Liverpool. He overhauled an antiquated laboratory and by installing cyclotron made it an important center for the study of nuclear physics.
During the Second World War, Chadwick carried out research as part of the Tubulos project to build an atomic bomb, while his Manchester lab and environs were harassed by Luftwaffe bombing. When the Quebec Agreement merged his project with the American Manhattan Project, he became part of the British mission and worked at the Los Alamos Laboratory and Washington, D.C. He surprised everyone by earning the almost complete trust of project director Leslie Richard Gross Jr. For his efforts, Chadwick received a knighthood in the New Year's honors of 1st of January 1945. In July 1945, he weaved the Trinity nuclear test. After this, he served as British scientific advisor to the United Nations Atomic Energy Commission. Uncomfortable with the trend toward big science, Chadwick became the master of Gonville and Caius College in 1948. He retired in 1959.
Free neutrons, while not directly ionizing atoms, cause ionizing radiation, so they can be biological hazard depending on dose. A small natural flux of free neutrons exists on Earth caused by cosmic ray showers, and by nature radioactivity of spontaneously fissionable elements in Earth's crust. Dedicated neutron sources like neutron generators, research reactors, and spallation sources produce free neutrons for use in irrational and in neutron scattering experiments.
The chemical properties of an atom are mostly determined by the configuration of electrons that orbit the atom's heavy nucleus. The electron configuration is determined by the charge of the nucleus, which is determined by the number of protons or atomic number. The number of neutrons is the neutron number. Neutrons don't affect the electron configuration, but the sum of atomic and neutron numbers is the mass of the nucleus. Atoms of a chemical element that differ only in neutron number are called isotopes. For example, carbon with atomic number 6 has an abundant isotope carbon-12 with 6 neutrons and a rare isotope carbon-13 with 7 neutrons. Some elements occur in nature with only one stable isotope, such as fluorine. Other elements occur with many stable isotopes, such as tin with 10 stable isotopes. The properties of an atomic nucleus depend on both atomic and neutron numbers. With their positive charge, the protons within the nucleus are repelled by the long-range electromagnetic force, but the much stronger but short-range nuclear.
Neutron numbers are called isotopes. For example, carbon with atomic number 6 has an abundant isotope carbon-12 with 6 neutrons and a rare isotope carbon-13 with 7 neutrons. Some elements occur in nature with only one stable isotope, such as fluorine. Other elements occur with many stable isotopes, such as tin with 10 stable isotopes. The properties of an atomic nucleus depend on both atomic and neutron numbers. With their positive charge, the protons within the nucleus are repelled by the long-range electromagnetic force, but the much stronger but short-range nuclear force binds the nucleus closely together. Neutrons are required for the stability of nuclei, with the exception of the single-proton hydrogen nucleus. Neutrons are produced copiously in nuclear fission and fusion. They are a primary contributor to the nucleosynthesis of chemical elements within stars through fission, fusion, and the neutron capture processes.
The neutron is essential to the production of nuclear power. In the decade after the neutron was discovered by James Chadwick in 1932, neutrons were used to induce many different types of nuclear transmutations. With the discovery of nuclear fission in 1938, it was quickly realized that if a fission produced neutrons, each of these neutrons might cause further fission events in a cascade known as a nuclear chain reaction. These events and findings led to the first self-sustaining nuclear reactor.
Free neutrons, while not directly ionizing atoms, cause ionizing radiation, so they can be biological hazard depending on dose. A small natural flux of free neutrons exists on Earth caused by cosmic ray showers, and by nature radioactivity of spontaneously fissionable elements in Earth's crust. Dedicated neutron sources like neutron generators, research reactors, and spallation sources produce free neutrons for use in irrational and in neutron scattering experiments.